So one way of phrasing this is what's called the representation independence theorem, sometimes called that. I'll phrase it a few different ways, but I'll start with this way. So if we have some field phi, which is equal, we can set it equal to some combination of other fields. So phi and chi can be scalars, let's say. And this function f, which could be fairly complicated, has to have at least one property that when chi is 0, it's 1. So that phi is and chi both show up linearly in some term in the function. If you like, if you want to think of it as a Taylor series, for example. So if that's true, the statement of this theorem is that observables, calculations of observables that are done with phi, or the Lagrangian that's made of phi, and what that really means is that I've quantized phi, will give the same results as those with a Lagrangian where I quantize chi, where I construct that Lagrangian by just making this change of variables. And we're going to exploit that fact in order to argue that we're allowed to do what I just said. So we'll start slowly, then we'll build up, then we'll state a more general theorem than this one, and then we'll show you how to prove it. So let's start by thinking of an example. Examples are always good. And we'll stick with our scalar field theory. I'm getting tired of writing factorials, so I'm choosing a little bit of different normalization here. So I'll consider an effective theory that has these terms at least to start. And eta has dimensions, and it's a small thing. It's like a 1 over a lambda nu. And the statement that we want to explore is the fact that we can use the equation of motion to effectively drop the last term by using the equation of motion. So how do we make use of this statement? Well, the idea is that we can make, this tells us that we can make changes of variable and that we won't change anything. So we try to make a change of variable to make this go away.
But sorry, that's not even the tree level equation, right? So you still have the lambda term.
Yeah, that's true. Yeah. Yeah, I should write the lambda term in there. Plus, minus, whichever it is. Thanks. There's a 2. Oh, thanks. All right, so how do we get rid of this last term? Well, let's just use our theorem by making a field redefinition. So I claim after making this field redefinition here that something magical will happen, or something that we want will happen. I'm going to integrate by parts at will, which is often a convenient thing to do when you're making these field redefinitions. So the term that's a half del mu phi squared goes to half del mu phi squared from the first term. And then we pick up a term that's exactly of the form we want to kill this extra term here that was proportional to del squared. And then there would be order eta squared term. We have to consistently make that field redefinition everywhere, so do it for the mass term as well. And let me write out the eta term here, just the eta squared term, just so we have all the terms. And we keep doing that. So we would do it also for the lambda phi 4 term, and we do it for this phi 6 term. And what you get out when you do that is that you can write down the Lagrangian, and you can group together the terms. And that operator is gone. So I got canceled by this guy. There's also these other things that are induced. But really what that does is it gives you more terms that are phi 4 and more terms that are phi 6. So you can really think of the other terms as just this guy here is just adjusting the constant of the phi 4. So from it's no longer lambda, it becomes a term that has this extra piece to it. So I'm going to give you more on this on the problem set. On the problem set, you'll work out explicitly what these relations are. And I'll also, on the problem set, let you think about what's going on here when you start considering loops in this particular example. I'll ask you what's going on, ask you to show what's going on, and that it's still OK when we have loops. So rather than explore this example in more detail, which I'm asking you to do on your problem set, let's state a more precise definition of what we're doing here. So that's the idea, that I can make a field redefinition. When I make a field redefinition, it's always going to induce something from the kinetic term, because the kinetic term's there. If there's a higher order term that's proportional to that kinetic piece, then I can set up my field redefinition in order to cancel it off. So there's some things that are important here. We have to make a field redefinition that preserves symmetries. So if we make a field redefinition that breaks Lorentz invariance, you can't expect that you're going to have a Lorentz invariant description after that. And this statement of f of 0 being 1 is the statement that you have to preserve the same one-particle states before and after the field redefinition. And such field redefinitions basically allow the classical equations of motion to be used to simplify the theory. I'll also put the proviso in that it should be a local quantum field theory. And there's no statement in this theorem that we have to stop without considering loops or without considering propagators. It can really make this argument holds even beyond the level that we've showed it, but with loops and with propagators in the as well. So there's some references. Again, I've posted the one that is closest to our discussion, which is this paper by Arzt. There's also a classic paper by Howard Georgi on what's called on-shell. The title of the paper is On-Shell Effective Field Theory. But I'll mostly follow the notations in this paper by Arzt in our discussion here. We'll go a little further than he does and elaborate a little more, but it's basically the same notation. OK, so how do we prove something like that? So there are some lessons in this proof, so it is worth something that it's worth going through. So the way that I set up my example up there, I was power counting in eta. Eta was 1 over lambda nu. So let me just write our effective theory organized as a series in eta. And let's consider removing some operator that looks like we should be able to remove it by making a field redefinition. And I'll try to be a little bit generic about what the form of that operator is. So I'll say it's covariant derivative squared acting on a scalar field, just again to make things simpler, but then multiplied by any function of all the other fields in the problem, and that's what t is. So phi is a complex scalar, and t is any function that sort of meets the needs of our symmetries of the problem. And I'm just using this other phi as a shorthand for all the other fields that we might consider. So there could be fermions, other scalars, gauge fields. So say we want to get rid of an operator like that. Oh, I should also say that it's local. All right, well, let's write down the generating function for this theory. Path integral over the fields, exponential. I'll regulate the problem with dimensional regularization. It's convenient. It preserves the symmetries. That's something we want to do. I write out some terms in the Lagrangian. We won't need L2. We'll stop at L1. But the idea, if we were to think about L2, would be similar. And let me write it as adding and subtracting something. So I'll subtract td squared phi and then add it back. So this is, if you like, you can think that L1 had a td squared phi, and what I'm doing here is removing it. So this is what we want. OK, so I'm just making it explicit, but still writing things in terms of L1. So there's that. And then there's the coupling to the source. And kind of in a generic notation, for each field phi k, I have a source jk. And I truncate everything at order eta. OK, so that's my starting point. And then Green's functions are obtained by functional derivatives with respect to the j's. All right, so what we're going to do is going to make a change of variable in the path integral. So of course, there's additional complications beyond what we were doing when we were just thinking about it at a Lagrangian level. And there's basically two additional complications. When we make a change of variable in the path integral, we're going to change the Lagrangian. We're also going to change the measure. So there could be a Jacobian. And we have to worry about what happens with the source term. So let me just think of it as a change of variable in the phi dagger. That's why I thought about I wanted to think about a complex scalar, so I could think about it as phi and phi dagger and just make the change of variable in the phi dagger. But doing a real scalar is just, everything would go through just as well. So there's one term, which is the phi dagger term, where there's a Jacobian factor. So here's that promised Jacobian for making that change of variable. Since the change of variable is order eta, it's not affecting L0. And I can write in a kind of nice notation, the way that these eta t terms from this change of variable show up, I can write them as taking all the terms in L0, looking for a phi dagger, that's the derivative, and then I replace it by an eta t. Now, some places in L0, there won't be just a straight phi dagger. There might be a del mu phi dagger, right? So I can take that into account as well. By taking the functional derivative with respect to del mu phi dagger. So any del mu phi dagger term, if I integrate by parts and then take the derivative, you can see why this is the right form. The integration by parts is what gives the minus sign. OK, so this finds all the phi daggers in my L0 and sticks in a eta t to order eta, which is the order we're working. So any time that we had an eta, which is these terms here, then we would induce something order eta squared. So and we're dropping those terms, so that's not something we have to worry about. And then there's the source, and one of the sources is for phi dagger. So for that particular source, j phi dagger, we induce a term that's j phi dagger eta t. OK, and then plus order eta squared. So as I said, there's three types of changes. There's a change to the Lagrangian, like in the example we did before. There's a change to the Jacobian through the Jacobian. And then there's a change through the source. We have to worry about whether any of these things will matter. And basically what the claim is and where we're going is that considering the Lagrangian is actually enough, so that 2 and 3 are something that we can kind of deal with generically. And then we only have to check that changing the Lagrangian does what we want. So the claim is, and what we'll show, without changing the S matrix, we can remove considering 2 and 3 rather generically. So we don't have to worry about them. So some of this we'll do next time. But let's just start today. So let's first look at del L, kind of analogous to what we were doing in our example before. So what we need is a change of variable, which is this one up here. And one restriction on delta L, which I mentioned as part of the assumption, was that this change of variable should transform in the same way as the original phi dagger. So same Lorentz index structure, same gauge index structure, et cetera. So that's kind of an assumption that we said. in order to respect the symmetries and not mess them up with our field redefinition. We assume that. So let's see what happens to L0. So there's L0 for, maybe it has some other terms as well, but let's just consider these pieces and ask what happens with them since they're the relevant ones. So when I switch to prime fields, I get that back again. I get m squared phi dagger prime, phi prime. And then I get some new terms, which I integrate the covariant derivative by parts, which I'm always able to do. It's nice what gauge symmetry allows you to do. Then I get a term like that, and I've set things up so that this term here does exactly what we need. If I go back over here, those terms are canceling. So OK, so that's good. Now, you may be worried about all the other terms that get induced. You've removed something, but you've induced a lot of stuff. But the point of the effective theory is that you already wrote down every possible operator that was consistent with the symmetries. So even if you induce a bunch of other terms, they should be terms you already have. So all you're doing with inducing those other terms is shifting the coefficients of the theory around. So L1 was already complete in the sense of having all the terms allowed by the symmetry. And we've respected the symmetry in the way we made this field redefinition. So any terms that I didn't write, which are all these terms in the dot 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 prime, are already operators that are present in the other dots that I didn't write. OK, so there were some dots here. There were some dots there. Even if I include operators in those dots, the operators in these dots are already present in those dots. And so all I'm doing really is shifting couplings. OK, and that's same effective theory, just with a new name for the coefficients. But we haven't fixed the coefficients yet anyway. We're setting up our effective theory. So whether we fix the new coefficients or the old coefficients, it's perfectly fine. So number 2 is the Jacobian. And I won't go all the way through this, but what are we going to do there? We're going to use the same kind of trick that we did in gauge theory. We're going to write the Jacobian as a Lagrangian involving ghosts. So remember when you talked about Faddeev-Popov in some field theory course prior to this one, you saw that you could write a determinant as an exponential involving some ghost fields. And the way that it worked is that up to a sign, whatever was sitting here ended up just sitting between the ghost fields. So this is the ghost of Faddeev-Popov procedure. And we're going to just use the same thing, although our ghosts aren't, we're not we're talking about scalar field theory. So for us, we take this guy, which is the Jacobian. I'll take that derivative. And if you take this thing, which is sitting in functional determinant, and you turn it into ghosts, then what you get is a term in the Lagrangian that looks like that. So that looks like it could do something, but it turns out that this term, and I think I'll take this up next time, it turns out that this term is actually a ghost that has mass that's of order the high scale, lambda nu. And so again, because of our logic of the effective theory only being valid below that high scale, we can just effectively integrate out this ghost, and then it shifts coefficients again. But I'll continue with that next time. So we have to figure out what to do with this ghost Lagrangian, and we'll deal with that next time. So any questions about our halfway done proof? No. OK. So this is a pretty powerful thing that you can use in effective field theory. And it also keeps your eye on the ball because it tells you to think about physics. Because this leaves physics invariant. It doesn't leave something like, if you say you had a theory that had some long distance degrees of freedom and it has some short distance potential. The short distance potential could be changed by a field redefinition. It might not be a physical thing. So you have to be, it keeps your eye on the ball as to what is physical and how to talk about things.